Thank you so much for introducing me, as well as thank you to Tatsuhiro for giving a good introduction to this topic of optical AI acceleration. I want to take that and then move into a discussion about how silicon photonics can enable both optical AI as well as edge computing. So I guess let's start with the fact that, as Hiro mentioned, the currency of AI is math. So if you look at any kind of AI algorithm out there, whether it's a generative neural network, underneath the hood, there's always going to be some deep neural network, which is a sequence of layers. So what's shown up here is a transformer neural network. That's the basis of generative AI, like ChatGPT. But it's just a sequence of layers. And within each layer, you have this critical element called matrix vector multiplication, which in turn is just an array of these arithmetic operations that we call multiply accumulates, or MACs. And a MAC is just, it's a very simple piece of arithmetic. You multiply two numbers, A and B, and then you add that to a third number, C, and then I guess you write the output back to the original register for C. And you can think of any kind of neural network, no matter how complex, as just being a string of MACs. All right, so we've been doing this for a while, and how we currently do all of this arithmetic is through digital logic. So we write all of our numbers in terms of binary representations, think 11101 or so forth, and then we perform these multiplications and these additions through a sequence of digital logic gates, like the adder and the multiplier, that are shown over here. When you do it this way, you have a really great advantage of precision, but you also have a disadvantage of overhead. So just to multiply these two numbers and add them up, that requires a total of, at a low bit precision of 8 bits, it's about 320 logic gates, or that's around 2,000 transistors. So there's a big overhead here. And so digital is great. You have all the advantages of Moore's law, but you also have this big overhead, this factor of 1,000 overhead, which is a real killer for a lot of applications. And now with Moore's law slowing down in recent years, as well as this growing energy consumption bottleneck for AI in general, the real question is, how do we push forward and think outside the box? Well, one thing we can do when we push forward is to go back to the past and think about what people did before there was digital logic. So one example is, if you go to analog logic, for example, there are these things called mixers, which can be used to multiply voltages. And at a naive level, you might think, well, a mixer can be done with only 4 active components rather than 1,000, so potentially it can be more efficient. And back before there were computers, this was actually the case. So mixers are an essential element in what's called a super heterodyne receiver, which is the basis for all modern radios. However, they are not used widely in computing for the reasons that you might have this low overhead, and they might potentially be fast, but you also have a very high power consumption. And they tend to have nonlinearities that are not ideal for logic. And so the result has been that for the last 50 years of computing, progress has generally been done with digital circuits. But our question is, can that change in the future with the advent of photonics, and especially integrated photonics? And I think that the answer is yes, thanks to some new innovations that have also been based on old ideas. So back at that time, back in the 20s, when Armstrong and Westinghouse were commercializing the super heterodyne radio, at the same time, Albert Einstein had won the Nobel Prize for his understanding of how the photoelectric effect works. Now, the photoelectric effect is a form of self-mixing, where you have light, it's an oscillating electric field, and then it creates a current of electrons. And you have this equation, I equals E squared, which is just a relationship between the electric field and the current. And you can combine the photoelectric effect with the wave nature of light. So the idea that you can send light through one example is you send light through 2 slits, and then you see an interference pattern. You combine that with the photoelectric effect, and you can create something called a homonide detector, which is a device that functions as a mixer, but at a much higher carrier frequency dictated by the optics rather than the electronics. So here I have 2 optical signals, A and B. I send them through this device, which consists of a beam splitter and some detectors, and I do a MAC. I multiply those 2 signals, and then I imprint that multiplied signal, and then I add that up to the voltage that's on this floating gate. And I can do that with time multiplexing, as well as wavelength multiplexing, using the many wavelengths that you have available in optics. letting you do many macs for the cost of one using a single device. So this is now a kind of mixer that might actually be useful for logic. It can work at very high frequencies. It can potentially be very low power. You can, if these detectors can be quantum limited, meaning few single or few photon, it has much less distortion because you have linearity that's guaranteed from this squaring law, which is physics. That's not engineering. And finally, this is a highly scalable device. So I hold here in my hand a very old phone. I think this is an iPhone 7. And this has a 12 megapixel camera or so. And you have 3 colors. So that's a total of at least 40 million photodiodes just in my phone. Each one of those things can perform this functionality. And it's not just detectors. There are other ways in optics to mix signals. A good example is nonlinear optics with thin film lithium niobate. And after this talk, you're going to hear a great discussion with both Kazugomi and Tim McKenna about NTT's work in NTT's research in developing a Tiflin foundry, which will push this forward. But regardless of how you implement this mixer, a big insight is that photoelectric mixing allows for a delocalized MAC. So in other words, if you have an optical network, you can take the activations and the weights for your neural network that you want to run from very different points of the network. Now, this is a bit of an exaggeration. I don't think the network would actually be this wide. But for example, you might have the weights of the neural network pulled from Hokkaido, and then from Kyoto, you get the activations, which might be some voice, something like "Sakura wa kirei desu ne." And I'm sorry, it's been a long time since I studied Japanese. And with that, I think that idea of delocalized computing together with photoelectric mixing is potentially a solution to this edge computing problem that we're seeing a lot nowadays, where we've moved from the PC era to the cloud era to the IoT era. And people like to say that we're swimming in sensors and we're drowning in data, and all that data is generated at the edge devices, which is far from the cloud. And you don't want to send all that data back to the cloud for processing, both because of privacy, also latency, and network issues. And we think that there's this photoelectric mixing scheme allows for a new form of what I would call magic state optical computing, which in contrast to desktop computing, where everything stays local, or cloud computing, where you just offload that local computing to a separate processor, involves a cloud that generates these physical objects that encode the algorithm. We like to call these magic states. It comes from some quantum background, but the idea is that if you have this magic state that encodes your algorithm, in this case the weights of your neural network, you send that to the user, and then in combination with a coprocessor, that user is able to process data locally without the latency and privacy issues of cloud computing, but also with low energy. And it's an idea that came originally from quantum computation. The idea is that you want to perform hard quantum gates on unknown data, and you can swap out the hard gates with generating these hard states that we call magic states. And that lets you also split up quantum computers into magic state factories, and then also the things that use those magic states for actual computation. So in collaboration with MIT, we've worked to develop this scheme called Netcast, which is a form of classical magic state deep learning based on photonics. And it involves two things. One is a server, and the other is a client. The server generates these optical signals, which are states that encode the weights of your neural network, and it sends those to the client. It does so using a combination of wavelength and time multiplexing, and the client uses mixing on this modulator together with demultiplexing to effectively perform the matrix vector multiplication of all those MACs that you need in a delocalized fashion with the weights that come from the server. And this is also not just a theoretical proposal by this point. We've implemented this in real hardware. So this is an example of a silicon photonic chip that we had taped out and that we used for our weight server to generate this magic state encoding the weights of our neural network. Once we generate that, we want to show that it's possible to do truly delocalized computing. So this is a map here of the Cambridge-Boston area. And you see that's where I work over there at MIT in Cambridge as a visiting research scientist. And this is Lincoln Lab over here. And we generated the magic state over at MIT. And then we sent it over to Lincoln Lab over some deployed municipal fiber. And because that wasn't far enough to show a really delocalized demo, we decided to send it back over loopbacks so that we get a total of 86 kilometers travel. It comes back to MIT in some other lab, and then it's processed using a combination of off-the-shelf telecom equipment, but you could also build this thing on a chip. And this is going to be the only data side of my talk, but we're scientists, so we work with data, and so I'm proud of my data. What's happening here is you have some weights from the neural network that are being fed into the client. So this comes over the fiber. They're being mixed with the activation data. In this case, this is an image that we want to classify. And then you do some time integration, and you end up with the result. This thing looks like a line, and it should look like a line because this is a calibration curve. And the deviation from that calibration curve, that tells you how accurate your computation is. So a big criticism of analog computing is always that it's not accurate enough. And what we show here is that you can do computing to at least 8 bits of precision. And that 8 bits is a pretty magic number, because most inference on GPUs nowadays, if you really want to push the performance, is about 8 bits. And so we can match that performance in photonics, but now with all the advantages of photonics. In addition to that, we've also been exploring the limits to energy efficiency for these devices. And one of those is the optical energy efficiency. And we've shown that fundamentally, fundamentally, you can perform computation with as low as 1 photon per Mach. So that's an energy efficiency that's 10 times higher than what you would, or 10 times better than what you could get with state-of-the-art CMOS electronics nowadays. So that's not the total number, but that's I think, more of a vision of what you could get in theory. And so, concluding that, I'd like to invite Shomil to the stage to talk about how silicon photonics can play in with this in terms of accelerating next-generation edge computing. Shomil?
Hi, so thanks very much, Ryan. So my name is Shomil. I recently joined Phi Labs as a postdoc. And so I'll talk a bit about what I think is a really exciting trend towards being able to build much more complicated optical systems for accelerating computing. And so, you know, a long time ago, if you wanted to build optical systems, you'd have to build it on a tabletop. So you'd take a table and you'd start building these complicated systems of lenses and mirrors and optical components, and you have to align them. And the trouble with this always was that it's very hard to scale these up to very large numbers of components. You have to align it, you have to keep it stable, and it would consume lots and lots of power. And over time, we've been able to scale up the complexity of these optical systems by basically miniaturizing the form factor. So we began with bulk optics, and then eventually we were able to miniaturize these into fiber, so fiber optics, and that really drove a lot of the innovations in the telecom industry. And really excitingly, over the last 20 years, there's been this shift to what is called integrated optics. So being able to integrate optical systems onto the surface of a chip. And one very particularly exciting way of doing this is what's so-called silicon photonics. So what silicon photonics is it's basically fabricating complicated optical systems using CMOS, which is the same manufacturing process that's used to create integrated electronic circuits. And so what you found as you look at these systems is you have this trend from going very large systems, physically large, that are high power, a few devices, to being able to really complexify these systems and realize large optical systems that are low power and many devices. And what you see, and this is the same trend that we've noticed in electronics with Moore's law, is that there's been a gradual, exponential increase in component count on chips, which has improved capabilities of these systems. And you see the same thing in silicon photonics, where by basically leveraging the same manufacturing processes as electronics, we're able to get this exponential increase in component counts in optical systems. And what that's really enabled is it's really enabled silicon photonics to take off as a platform for making complicated photonic circuits, not just for communication, but for also computing and LiDAR and many other applications. And so this enables the exciting possibility of being able to create fully integrated photonic chips that are processing neural networks in optics. And what this enables is new kinds of applications for machine learning. So for example, systems like autonomous navigation, so self-driving cars, or telecommunications, or astronomy, where you want to be able to intelligently process data that's directly in the optical domain. And oftentimes, you want to do this very fast. So you want to be able to get very low latency, so microsecond and nanosecond processing of optical data. And if you're able to build a system that computes in optics, you can have opportunities to build systems that basically compute by propagating light through a system. So let's say I have some system, like a photonic processor for machine learning, where I want to classify images of like a dog. And so you can encode that image onto optical signals, onto light, and basically by the process of physically propagating through this system in optics, you compute. And you have your system tell you, oh, this is a dog. And so this led us to consider the question, are we able to build chip-scale systems that process DNN models entirely in optics? And so this is a system developed in a collaboration with MIT where we did this. So we created a photonic integrated circuit fabricated in a commercial silicon photonic process that realizes neural network processing entirely in optics. So we were able to encode data onto the optical domain. We do all the computation, both linear and nonlinear computation optically, and then we're able to read out. And what's very nice about this is that it's very fast. So we're able to classify signals in this chip in optics in less than half a nanosecond. And what we do is we run some speech processing tasks with this. And what we find is that when we train neural networks onto this device, we're able to perform classification of vowels with very high accuracy, so 93% accuracy. And what's very exciting about this is it's the same accuracy as we get on a digital system. So we're able to get comparable performance to a neural network run on a digital computer. And so with that, I'm going to wrap up. And so hopefully, this is giving you an idea of what are some of the really exciting possibilities that we're able to realize using integrated photonics. So it's a really exciting time to be in this space. Many established applications are maturing, like telecom and sensing and datacom. We're able to use CMOS infrastructure that's already been developed over decades to realize complicated optical systems. And this can enable many new applications, not just in AI, but in edge computing, icing machines, other kinds of computational systems, and even quantum computing. So great, thanks very much.